Hi, thought we could look at the simple circuit, a amplifier circuit, and it's not a tutorial, it's just a exploration that I did, because on the Facebook there was a guy who asked about the Cell Super 12, which is one number higher than the one I have. It's from 75 and mine is from 73. Anyway, he was asking, so he says he measures 2 volts here, 1.4 and 1.5 volt, and then he says that this is for both the channels, it's the same for both channels, and it was over here, not here, but over here, and the fault is around here somewhere, or the signal is almost gone here. So and when you measure DC, as you can see, this value here is much lower than he measured, and also the difference between these two values are much different. That means that this transistor in the schematic with these values will be in liner mode, but with these values then this transistor is in saturation. That means it's closed, it's like a switch, it is closed, so if you put a signal in on it, not much will happen on the output. Maybe you will get clipping sounds. So the first thing I did was to put the schematic into LT-Spice, and you have the same power supply arrangement with the resistor coming in, and I have ignored every capacitor, therefore this circuit looks much simpler, but it's actually the same from a DC standpoint. That means from a direct current standpoint. So what I wanted to see was how stable this voltage was if I changed the voltage supply. So one way to simulate that was to do a DC sweep. So a DC sweep, usually you have seen me do transient response. That means you see what happens over time. But a DC sweep, then you can say, okay, I want this source, which is V1 over here on the left side. I want that to go from 0 to 40 volts, and when I run it, then I can then look at nodes and see what happens. So on the bottom here you can see, it's a bit small, you can see 0 to 40 volts, that's a bit high, but anyway. And the green trace is now where I'm pointing here. And you can see the voltage goes up when the source goes up, and when it's the transistor is turning on, then it regulates. So I was wondering, how do you get this flat line here? It's not perfectly flat, and well, that depends on the resistors around here. Another thing you can do is to calculate it, and I wanted to know how that was done. So but first I just wanted to doodle around with these components. So instead of saying absolute value here, you can say for example collector, and like this, right? And then I can say I want to simulate with a SPICE directive in steps with the parameter collector, like this, with a list which is, let's say 1K, 3K, 5K, 7K, 9K, just to have a list of different resistors. So what happens now is that it will run DC sweep, but we will do it over and over and over until it has done all of these values for collector. And now you can see what happens. Okay, so you see the transistor turns on here, and the lowest value, 1K, will then won't have so much voltage drop over it, so therefore the voltage will rise. So, but for 1K, 3K, 5K seems to be very close, and then you have 7K, which then is too much, and so on. So I wanted to figure out how do you calculate something like this. So let's go back again and make this into a comment, and then I'll just say 5K6 again and run it again, and there we go. They're back to the old settings. So what's actually happening here is that okay, when this voltage over the supplier is rising, the voltage over this one is rising just as fast, as you can see. So how do you select the resistor that rises as fast as this? So I've done some exploration, just trying to figure out how to calculate this. So the main idea I had was that I say that the change of voltage equals the change in current times RE, which is the voltage over, oh sorry, RC, which is the voltage over the collector. So I said the change in this voltage here is equals to the change in voltage here in respect to this voltage. And by doing that you have to do derivation. I think that's the correct word in English. So basically what you do is say that when these are equal, then you have this relationship that the rate of change is the same. That's what I'm thinking. So if you derive the VCC over VCC, then you get 1. Because if you derive something with the same, you get 1. So yeah, so I don't know how interesting this is, but please just follow me, and I will do measuring, and not just the simulation, but also actually trying it with. Yeah, so what's the main reason for having these 3 volts anyway? Well, the reason is to stabilize the DC levels and put this one into regulation and let it stay stable in regulation. But there's a problem though, because when you get a signal in which is AC, this resistor will provide a lot of attenuation, so the signal would not be amplified much. So what you do, you put a capacitor here such that the AC signal will have a path to ground. It basically bypasses this one, but for DC, this one will provide the stable voltages. So what was the fault anyway? As you can see, I have drawn the circuit, part of the circuit that was in concern, and I asked the technician to take some DC measurements. And the VCE voltage was 100 millivolts. That means that the device was in saturation. So I told them, I don't know what the fault is, but the transistor you have is in saturation. So I thought maybe it could be that biasing resistors, but no. As you can see here where I'm drawing, this is the only path where you can have DC being dragged up to 5 volt. So basically that capacitor was leaky. So another technician came in and said that maybe this one is leaky, and it changed it, and it works. So that's it. So you may wonder what's the point of all these resistors in the circuit. Well, the transistor alone is not very linear, or it's very unlinear, logarithmic. So by using resistor you tame it, and also from transistor to transistor this gain can vary as much as 100 times. But with these resistors none of that really matters. What matters is that the gain is high. So this is the end of the video. I'm inserting the measured values. You can see on the top row there I have all the measurements, and I'm filling in the last one now, the VBE, and you can see on the graph that the VRC, the red one, it's following VCC very closely, and that's what gives that constant voltage over VC, the yellow one. And you can see VE is increasing also in a linear fashion with the VCC. So, but let's zoom in on that. So first let me show you how to draw this schematic. It's very easy. You just press the diagram, and then you have to take XY plot. That's what I usually take, and points and lines. Next, check your data area, just mark everything there. So let's see what happened. Check that out. Very little effort to get that graph. So then let's move on, and this is okay. Let's move along and let's put the title. So this is a DC sweep of a VCC Yes, it's an inverting amplifier. So put that in the subtext, subtitle, or undertitle. The x-axis, the one on the below, that's VCC in volts, and the y-axis is just voltage. And that's it. There you have your graph. So let's try and make it a little bit bigger. So let's also change the axis. Now I'm formatting the axis, and you have to switch to automatic, so you can write. So now I'm changing the range to only display between 5 and 0 volts. Now you can see more clearly what happens to this low voltage stuff. There you go. The VBE and the VE. So there you have it. So the VBE, that's the diode inside the bipolar junction transistor. So you can see that it clamps around 0.6, 0.7 volts. Yeah, thank you for watching. Hope that was interesting. So, see you another time. Bye bye.